Today, we're going to be speaking about performance optimizations for Java applications. And my name is, Aaron Wanjala, and I am the Java developer advocate at Google Cloud. Prior to becoming the advocate here, or the Java advocate, I was, a regular Java developer. And when I was on a team, in an org, in a sprint, it never really made sense for me to take time to look at what was happening with different JDK vendors or frameworks as far as performance optimizations, to hold that in mind because the problems didn't come up that often. And that led to me not having them on hand when I needed to apply them to a slow project or a workload or web service. And so the idea of this talk is that I, now that I'm an advocate, have the time to sit back and keep up with where these different optimizations are on their release trains with different frameworks and in terms of their readiness and usefulness, and prepare that information for you in an easy kind of practitioner level bite-sized package so that you don't have to do the legwork and can just have it in mind when your problems arise. So to get started on this topic, we're going to start with the word optimizations. Again, the wrong way. It's a broad term. You could kind of land a plane on the word optimizations, hence the iceberg there. But I just want to talk about what I mean in this context by optimization and what we'll be focusing on today. Because there's a significant difference in how I would approach optimizing a slow call within an app versus a slow app that's starting up in general versus an app that's building slowly. And so in my experience, there's kind of three broad classes of optimizations that are worth keeping in mind when you're going to approach how to address them. And so I would say that there's a build time optimization where you have the app code together, you're looking to ship an image or a jar. That's one class of slowness. Another class is runtime. When the app is up and running, it may have been running for a long time. It may have run the same operation tens of thousands of times. And this is where things like JVM optimizations can come in and offer performance boosts. And then there are start time optimizations, which are closely related to the hot topic of cold starts, where you may be in a serverless context, you may need a container to start up very quickly and perform within a certain amount of time when a customer is waiting on the other end. And I would say that within those different problem sets, there are different optimizations that should come to mind and approach the problems differently. So I think they're useful categories. I should also say that the format of the talk is going to be me going over a few of my thoughts about this type of work. And then I invite you to come up afterwards. There's going to be plenty of time for Q&A. There's a microphone in the middle. And if you see value in this kind of preparatory work, please let me know. If you have any questions about these optimizations, I'm happy to answer them or get back to you on them. Another tool that I use to sort of assess how I would approach fixing a slow workload is with this sort of flowchart. So at the top, we have a slow workload that I'm being presented with. And I ask myself, when is the app slow? Is it in the build time category, start time category, or runtime category? If it's in the build time category, then my first approach is to ask myself within the org, like say I'm working at a bank, are our dependencies changing very often? Or are we tied to certain verified artifacts that we're pulling the same way every time? If so, there's an opportunity there to not have to pull and build the same layers of the same containers over and over again with tools that offer layered builds, which we'll get into in a minute. If, on the other hand, there is a runtime inefficiency where there's a hot path in the app and it's just kind of algorithmically slow, that's a more ambiguous class of problem to work with. My first stop is always tracing, and then you kind of have to apply case-by-case optimizations. That is a topic all on its own that deserves its own talk. There's a lot to be done with tools like CloudTrace to offer performance gains. But the bulk of the time we'll be spending here is in the start time optimizations. So a helpful question that I like to ask with the new and emerging optimizations is this a long-running workload? I feel like that helps me pick between different optimizations, because if it is a long-running workload, or if it is not a long-running workload, then an optimization like native image compilation may be a good fit. It's great for optimizing short workloads. There's a set of trade-offs involved, which I have spoken and written about quite a bit, especially last year. I can share my blog posts on that. But if you do have a long-running workload and you want something like the optimizations that the JVM can have for running over a long period of time and running the same operation over and over again, then you may not want to adopt the closed world conception and throw out the JVM with native image compilation. Instead, you may want to take an approach, one of two approaches, based on another question, which is, are you running many instances of the workload? If you are, then you may be leaning more to class data sharing, and if you aren't, then CRaC may be a good option as well. Now, for myself, a lot of these projects were not top of mind when I was working as a developer most of the time, because they just didn't come up that often. But I'm going to take you through my journey of familiarizing myself with these, trying them out, seeing the situations where they offer good performance gains and where they offer fewer performance gains. And hopefully that will get you thinking on how to apply in your projects. So we're going to start with the build time optimizations. One option for a low effort but high yield build time optimization is using a build tool that we published in 2018 called Jib. It's an alternative that is daemonless, produces fast reproducible builds, and does not need an installation to get started. You can actually just run it from a Maven coordinate if you don't want to change your project's POM. So it's an open source project, and in order to, well, there are lots of people talking about it in the community and how it is an option on par with containerization methods like Spring Boot's built-in build pack support. There's a wonderful article attached to that that's available in the slides from the Spring team. There are also significant performance gains in the layered versus non-layered image concept that I touched on earlier. So in the top left there, you can see the non-layered taking an Uber jar and putting it into a Docker file approach. Simple, it works, but you will be building that entire app, that entire container from scratch each time you change anything. If you change a single piece of app, a single line of app code, you're repushing the entire container with the entire jar rebundled. And as you can see that in the bottom left, it is in one big layer of 329 megabytes. Whereas if you take a layered build approach with the Jib coordinate there, shown in the top right, instead, Jib automatically dices up your app in a dependency layer, an app layer, and a libraries layer, I believe. And so that means that when you change your app code, only the thinnest slice, which is actually your app code, is being rebuilt and pushed, which if you apply it to a build server running hundreds of builds for an entire engineering organization, your savings are your time spent on each cached layer times the number of builds, which can add up quickly, especially if you're paying for that compute. So there's an overview on Jib as an option for layered building. Next, we'll be moving on to CRaC, which is coordinated restore at checkpoint. This is an emerging OpenJDK project being developed by Azul that defines an API for making use of your apps, or to allow your apps to make use of taking a running instance, creating a checkpoint, and restoring the same app in the same state from that checkpoint. So in a nutshell, it is restoring a Java app from a warmed up image. And the words warmed up are very important there. The performance results are compelling from CRaC's own publications. These are, if you're familiar with them, results on par with native image compilation, or near on par, with a different set of trade-offs. So it's a good option to keep in mind. Now, there are some considerations involved. It is still in a pre-general availability state. It is getting excellent support from frameworks, but it involves certain kind of early adopter steps, like using a specific Tomcat version that supports the coordinated restarts of a running image or a running application, which is a hurdle. But the experience of using it is actually relatively straightforward. You're able to run your Java app normally with a flag to say, this is where I want to save. That CRaC checkpoint 2 flag is defining a path where you'll be saving your checkpoint file. If you don't define that, I believe it stores at Java home by default. And then you use the JCMD command to restore from that checkpoint later with the CRaC restore from CR command. And so I'd say, in a nutshell, the limitations of CRaC are that it is still very new, very promising, but very new. It has improving but limited support. Currently, it only runs, I've only been able to get it to run on specific Linux distributions, not on Mac, not on Windows, which is likely not a problem for build or deployment servers, but likely an issue for developer machines. And then the third is, of course, the elephant in the room, dealing with the snapshot. And I'd like to take a minute to talk about that, because from the JDK perspective, the snapshot handling is being exposed as an API, and frameworks are picking up that functionality at an impressive rate. So soon enough, in Spring Boot 3.1, which uses Spring Framework 6.1, you'll be able to have Spring lifecycle hooks that can feed off of these snapshots and allow you to tell your app what to do when starting up from a warmed up image. So these things are coming soon, important to keep in mind. Now, and I'd like to underline that CRaC is a good option if you are not running several applications. So as opposed to class data sharing, which benefits from being applied to several running instances of the same app. So class data sharing is a feature that has been around in the language for a long time. One of the many things that I love about Java is the Java enhancement proposal process, which provides like a great historical record for the language, its features, and their improvements over time. And because of that, we can see that class data sharing as a baseline feature was established in 2004 in JDK 5. So concept is fairly old, but essentially you are taking an allowed set of classes and pre-processing it into a shared archive that can then be loaded into memory at runtime to reduce the startup time of other apps that use that shared archive. And of course, that can also reduce the memory footprint, because many apps can refer to the same class files with one shared archive. Many JVMs can refer to the same class files. So that reduces memory at runtime. And a walkthrough of the experience using baseline CDS is pretty straightforward. You use the share flag, and you have 4 options. Dump creates the archive. Off says do not use CDS. On says use CDS, and fail if you don't, like do not start if you can't use the archive. Auto means use the archive if and only if it is present in the place that you expect it to be. So interesting, straightforward, pretty simple. A few years down the line, we get application class data sharing in JEP 3.10. And so this is where the application class data sharing implementers came in and said, what if we extend CDS to allow other loaders, rather than the built-in system class loader, to do the same sharing trick to save memory at runtime and to be more performant? This means that it can amplify the benefits of the same class data sharing system. Now, it added another step to using the class data sharing feature. So you had to use app CDS to enable the feature. And then this is a helper function, the listing. It allows you to list the files that it would be loading at runtime to help direct you when you're trying to create your archive and make sure that you're dumping the expected list of files and then picking them up as expected later. And then finally, the using step is when you actually use the shared archive and get the performance bonuses that are promised. Fantastic. But as you can see, it's The performance benefits are significant. In the JEP, they quote start time reductions of 20 to 30% in some swing use cases. But we'll get to my findings in a minute here when I tried it myself. In JEP 341, though, which was not that far apart, and from 2017 to 2018, there was default app CDS became a goal. And so the idea with this improvement was to improve the out-of-the-box startup time for developers without having them have to take on the hassle of having to run Xshare dump and deliberately take all these other steps, hence making it the default. So I found this to be very promising, even though as a first cut it only targeted a subset of builds. It was only native 64-bit builds. But it's a step in the right direction and very promising for what comes next, which is dynamic CDS archives in 2018. Again, a lot of movement in the last couple years with these last two improvements. And so the goal here is to dynamically detect which classes are loaded out of a jar and which ones aren't, so that you're only loading the shared archived files that would actually be used between runs, and making the whole class data sharing feature transparent and usable out of the box without needing a whole bunch of steps and flags for you to take on, or fewer at least. And so this is the part where I would normally tell you, like, we're in the promised land and this is fantastically easy and usable, but it wasn't immediately clear to me how to get the benefits, because when I tried it, I ended up getting vanishing returns, or in some cases, negative returns. And that was despite the fact that I was able to prove that it was using the loaded files. But the issue was that I was really only running a single instance of a single application, or I wasn't running enough instances of the same application. And so this is where the shining example of this is an application where you can put up multiple instances and have many, many JVMs benefit from the same shared archive files. Because otherwise it is really just having one JVM pick up and put down the same shared archive files. Not much of a performance benefit. So I would keep that in mind. And then finally, there's native image compilation. So native image compilation, for those who are not familiar, is engaging in a trade-off where you adopt ahead of time compilation, and instead of taking the classic Java use case of writing your application once and running it everywhere, where you write the Java code and it runs on a JVM on top of any architecture, instead you target a specific architecture at compile time and go directly down to bytecode, to a native executable. Sorry, not bytecode. So that means that you target a specific machine with a specific architecture, but you get near native performance as a result. This involves a number of trade-offs, which we'll be going into in a minute. And of course, the most prominent way to engage in this trade-off is with GraalVM, which is a high-performance JDK developed by Oracle. And in recent years, it's gotten fantastic uptake from frameworks like Quarkus and Spring, and that's why I think it's important for developers on Google Cloud to keep in mind, because it is no longer a hard-to-use kind of arcane optimization. It is being put in your hands by fantastic work in the open source community. So this all kind of came into general availability last year with Spring Framework 3, Spring Framework 6, and Spring Boot 3. And the benefits, as I would state them, are smaller artifacts. You get faster startup times because you are no longer shipping with a full running JVM. You're simply shipping the resulting native code. And finally, you have a smaller memory footprint because you're not shipping the JVM. Now, there are a number of, well, let me go over the benefits more. There are significant reductions in startup time and memory footprint. The graph on the right is from a blog post that I wrote last year, where in an average of 250 startup times, the native image compilation started up in 0.6 of a millisecond versus 132 for the same app on a JVM. And the time to first request had a similarly effective result. So rather than it just starting up and being technically available. That was a Spring Boot container that was ready to serve requests at the end. And that was on an E2 standard machine, which is roughly equivalent to a 16 gig MacBook. But there are a number of limitations to keep in mind, which are chiefly the closed world conception, meaning that you have to accept that your app is taking a snapshot of what is available on the class path when it compiles, and saying that aside from a few exceptions, nothing else is coming in. You're not loading in new classes, you're not loading in new resources from the file system. It is mostly a closed world conception without specific annotation to get around it. Another significant loss is that you are losing the hotspot optimizations. So the JVM is very good at optimizing long-running workloads, as many of you know. And so by giving up that JVM, it is advised that you do this in use cases where you know that this is not going to be running for a long time. In some cases, you may know that it's going to run for shorter than a single garbage collection cycle, and you can select a garbage collector that either doesn't run or make sure that it works well with how your workload is going to encounter garbage collection cycles. And then the last trade-off is that your build times are much longer, because they're much longer and they require much more resources because you're doing a lot more computation at build time. The interpretation step of taking your Java bytecode to the native instructions for the machine it's running on are an expensive step, and that's what accounts for the difference between Java performance and native language performance. And so you're taking on all of that cost right at the start for a much more performant native executable at runtime.